Welcome all. In this video, we are going to talk about the second law of thermodynamics, zeroth law of thermodynamics, and the third law of thermodynamics. Okay, first we will be seeing the second law of thermodynamics. There are many statements of the second law of thermodynamics. Okay, basically the entropy comes from the second law of thermodynamics. The entropy of the universe is continuously increasing. So this is one of the basic basic statement for the second law of thermodynamics. So the spontaneous process, as we have discussed in case of an entropy, the spontaneous process are accompanied by a net increase of entropy. So net increase of entropy. So that is also one of the statement for a second law of thermodynamics, that is total enthalpy change of the system and the surrounding. So that we call it as an entropy of the universe would be always positive, should be positive for a spontaneous reaction. So these are two statements, or we will be seeing another statement which is that energy. I think in the last part of the entropy we have discussed about this earlier. The energy of the universe is a constant. That's the first law. First law, energy can neither be created nor be destroyed. But second law says that the entropy of the universe is continuously increasing. So entropy is continuously increasing. That is again three statements which relates the entropy of the system. And regarding the heat, okay, heat of the regarding the heat, the second law says that the complete conversion of heat into work, that is whatever heat we are going to give to a system is not completely converted into work without leaving something behind. Like that's all the work is not converted, but probably as an mechanical engineering student, you might be studying about the Carnot cycle. Carnot cycle in your higher semester you will be studying, which deals with this statement. Okay, so you can't completely convert heat into work without losing some heat or leaving some effect elsewhere. So that is again a statement of the second law. So one of the drawback of first law says that energy can be transformed from one part to another, but it does not say whether it can be transferred from a lower energy content to a higher energy content. Basically it does not say whether heat can flow from a colder body to an hotter body. So here this statement in the second law it is clearly given that without the help of an external agency, a spontaneous process cannot be reversed. That means heat cannot by itself flow from a colder body to a hotter body. So heat cannot flow from a colder body to a hotter body. Okay, and another statement is that all spontaneous, that is thermodynamically spontaneous process. Spontaneous process means you know that it takes place on its own. Like it does not require an external agency to make the reaction happen or to make the process happen in a better way. So are not reversible, thermodynamically reversible. Once it has been done, it cannot be reversed. Reversible means in thermodynamics they will be saying a very small change. Okay, very small change which can be easily reversed. So that's not going to happen in the according to the second law for a spontaneous process. So these are the various statements of the second law of thermodynamics. Okay, we will be talking about the zeroth law of thermodynamics. Zeroth law of thermodynamics is basically a very primitive statement, okay, which says that when A and B are in thermal equilibrium, remember A and B are in thermal equilibrium separately, okay, separately, and B and C are in thermal equilibrium separately, and B and C are in thermal equilibrium separately, then A and C should be having an thermal equilibrium. A and C should be having a thermal equilibrium. Basically, if there is two bodies in thermal equilibrium and one of the two bodies is in thermal equilibrium with the third body, then the first body, and you can say all the bodies will be at the same thermal equilibrium or same temperature. You can say it's a thermal equilibrium in same temperature, same heat content. You can say some same heat content. So it basically says that systems that are in thermal equilibrium exist at the same temperature. Okay, so that is also one of the statement of the zeroth law of thermodynamics. Basically, if A and B are in thermal equilibrium and B and C are in thermal equilibrium separately, both of them are separately in thermal equilibrium, then A and C should be in thermal equilibrium. So this is about the zeroth law of thermodynamics. Third law of thermodynamics, interesting law, okay, which we have to be yet verified. Probably it should be correct when I say it is to be yet verified. It says that the entropy of a perfect crystalline solid, that's an rather an what do you call it, as an absurd way. I mean the word perfectly crystalline solid, because in a solid there will be some very minute thermal equilibrium, very minute what do you call it, as a motion, you can say translational motion or vibrational motion. Basically mostly it will be vibrational motion. So when the crystalline solid has no what you call as an no vibration, then it is called as an perfectly crystalline solid. So the entropy of the solid will be 0 when it obtains a perfect an absolute 0. Okay, when the temperature approaches absolute 0 Kelvin. So what basically it says, at 0 Kelvin the entropy is 0. At 0 Kelvin delta S should be 0. Okay, this is the basic statement of the third law of thermodynamics. All the motions of the solid stops, and the solid is said to be perfectly crystalline when it approaches 0. Okay, so there are other statements, same thing. They are saying all the statements has been given in the notes actually. So these are the this is the third law. Third law basically says that entropy of a perfect crystalline solid is 0. Okay, is 0. That is when the temperature approaches absolute 0. It will be a perfect crystalline solid without any motions, without any vibration, without any type of motions for a solid at a absolute 0. So this is for this video. We will meet in the next video. The topic would be partial molar property. Okay, we will meet in the next video. Until then, bye.